All right, let's jump right in. We're going to talk about a technology that could totally flip the script on our energy future. I'm talking about perovskite solar cells. The progress here has been, well, just off the charts. So let's get into what they are and, more importantly, why you should care. Okay, just think about this for a second. What if solar panels weren't just these rigid, heavy things on a roof? What if they were cheap, flexible, and super, super efficient? I mean, flexible enough to be part of almost anything. That's the dream, right? Well, that's the promise we're digging into today. So to really get it, you've got to see how they stack up against what we have now. Traditional silicon, yeah, it's the old reliable, the workhorse of the solar world. But let's be honest, it's got its problems. It's stiff, it's heavy, and making it is a pretty intense, costly process. But perovskites, they're like a totally different beast. We're talking cheaper to make, way more flexible, and potentially even more efficient. It's a whole new ballgame. All right, so let's get into our first big topic here. Are these things solar's next super material? For a technology that hasn't been around that long, the progress we've seen with these perovskite solar cells, or PSCs, it's been explosive. No other way to put it. And if you need proof, just look at this number, 26.7%. That's the record efficiency for one of these cells. Now, to give you some context, that's a huge deal. It took Silicon Tech almost 40 years to hit that kind of performance. Perovskites did it in about a decade. A decade. That insane speed is exactly why everyone in the energy world is sitting up and paying very close attention. So, what's the magic here? How do they actually work? Let's peel back the layers and take a look inside. Okay, so the secret sauce is the material itself, perovskite. And here's the thing, it's not just one thing, it's a whole family of materials that all share this specific crystal structure, this ABX3 formula. Think of it like a perfectly shaped Lego brick. This particular shape is not only super easy to build with, but it also happens to be amazing at soaking up sunlight and spitting out electricity. It's a perfect match.
The easiest way to think about one of these cells is like a high-tech sandwich. Seriously. You've got the perovskite layer in the middle, that's the good stuff, the part that actually absorbs the sunlight. Then it's squished between two other special layers. These are your bread slices, and their whole job is to collect the electrical charges that the light creates and get them moving. That's what gives you an electric current. Simple, right?
Okay, so we know what's inside, but how do you actually make one? And this is a really important point, because, making one amazing little cell on a lab bench is cool and all, but trying to make millions of them on a factory floor, that is a whole different level of challenge. In the lab, the go-to method is something called spin coating. It's kind of what it sounds like. You drop a bit of perovskite ink onto a surface, and then you spin it, like really, really fast. The spinning action spreads the liquid into this perfectly thin, even layer. Then you add another chemical to make it crystallize in a flash. It's great for making small, perfect samples for experiments, but for making giant solar panels, no way. It's just not practical. So, to get this out of the lab and into the real world, scientists are looking at methods that are a lot more like printing. Things like slot die coating or blade coating, they basically work like a high-tech squeegee, spreading a perfectly even layer of that perovskite ink. The goal is basically to print solar cells. But man, the challenge is huge. Imagine trying to get that layer perfectly uniform, just nanometers thick, over a massive area with zero mistakes. One tiny flaw and the whole thing's a dud. So yeah, scaling this up is a massive, massive hurdle. But all that stuff, the efficiency, the manufacturing, it all takes a backseat to the one big problem. The Achilles heel of this whole technology, the one thing holding it back from, world domination. And that problem is stability. Here's the heart of the issue. The perovskite material has a split personality. It can exist in two different forms. You've got the alpha phase, that's the good one, the black, high-performance version that actually makes electricity. It's exactly what we want. The problem is, it's kind of fragile. At room temperature, it wants to change into its evil twin, the delta phase. And the delta phase is this yellow, useless version that does absolutely nothing for solar power. And this is a great way to visualize that problem. Think of the awesome alpha phase as a ball perched right on top of a steep hill. It's in a high-energy state, ready to do work, but it's not stable. It's just teetering there. And at the bottom of the hill, in the valley, is that useless delta phase. It's the stable, lazy state. So naturally, the ball wants to roll down the hill. The entire goal of all this research is to figure out how to prop that ball up, how to lock it in place at the top of the hill so it stays in that powerful, useful state. And chemists are getting really, really clever about how to do this. They have a whole toolkit of tricks. One is called compositional engineering. which is a fancy way of saying they mix in different atoms. It's kind of like making a metal alloy. You add a little bit of something else to make the whole structure stronger. They also use different solvents to control exactly how the crystals grow. And one of my favorites, they add these temporary scaffolding molecules that help build the perfect structure, and then they just evaporate and disappear, leaving the stable crystal behind. It's pretty brilliant. Okay, so let's say we do it. Let's say scientists crack this stability problem for good. What happens then? What does that future actually look like? Well, this is where it gets really, really cool. Get ready for this number, over 30%. That's the potential efficiency you can get when you combine perovskites with silicon. And that number, it's not just a little better. It completely blows past the theoretical maximum efficiency you can ever get from silicon by itself. Think about what that means in the real world. You could get a third more electricity from the exact same amount of space.
So how does that work? It's called a tandem cell, and it's basically the best of both worlds. You take a normal silicon solar cell and you put a super thin, see-through layer of perovskite right on top. The perovskite layer is great at capturing the high-energy parts of sunlight, like blues and greens. Then it lets the rest of the light, the reds and infrared, pass right through to the silicon cell underneath, which is great at capturing that light. So together, they tag-team the entire solar spectrum. Nothing goes to waste. And that's how you get that massive jump in efficiency.
And once you have stable perovskites, the possibilities just explode. We're not just talking about better solar farms. We're talking about buildings where the windows themselves are solar panels. We're talking about flexible solar cells woven right into your jacket or your backpack, charging your phone while you walk. Because they're so light and powerful, they're perfect for satellites and space travel. And yeah, of course, you could also use them to give a huge power boost to every single solar farm already out there. It's a total game changer. So for decades, solar power has meant heavy, rigid silicon, but we might be standing right on the edge of a completely new era. Which leaves us with a pretty mind-blowing thought, doesn't it? Is the future of clean energy something we can just print?